In the last class, we discussed about the Gibbs paradox, and in that Gibbs paradox, we have seen the entropy of mixing or entropy change of mixing of identical gases, which is coming as greater than 0, as you can see here. From the equations. Okay, so by using the entropy equations, we considered initially we considered dissimilar gases, and we have seen that the delta S, that is change in entropy, is delta S is greater than 0 for that case, and that is good. And thermodynamically, for any irreversible process, delta S should be greater than 0, and it was okay for dissimilar gas, and we have seen that for delta S is equal to 0 for dissimilar gases. But when you consider similar gas, or if you consider identical gases also, we have seen that delta S is still it is greater than 0, but thermodynamically it is not possible, because when you consider identical gas, it is a reversible process. If you mix two gases and you separate after some time them by using a barrier, then you have to get the same condition, so that it is nothing but it is a reversible process. After some time, you can reconstruct the same situation after mixing also. So it is a reversible process when you consider identical gases, but by equation, if you are considering this equation, then you can get delta S is equal to 0, sorry, delta S is greater than 0 for the case of identical gases also, when you consider mixing of two identical gases also. But that is not true from thermodynamic point of view. So this discrepancy or mismatching of the thermodynamics with the statistical mechanics, or the entropy change that we calculated from these equations, which is called as the Gibbs paradox. Okay, now we understood that there is some mismatch from thermodynamics by calculating the change in entropy after mixing identical gases. So we have to solve this discrepancy, and for that we have to consider an additional term. Okay, so in this video, in this class, we will be discussing about remedy for Gibbs paradox. Okay, how we can resolve that problem, and so for that we considered delta S equal to k n1 ln n1 plus n2 by n1 and n2 ln n1 plus n2 by n2. This was our equation for change in entropy with the number of particles. Okay, change in entropy with number of particles. And this equation we have derived in the last class. You can see that class uh, for better clarification. You can check that. And then delta S, from this equation we can write that change in entropy of mixing of after mixing of gas. And if you consider the total entropy change means subtracting the total entropy from the entropy of mixing of that system, then you will get delta S. Okay, so this delta S can be written as k into n1 ln n1 plus n2 minus n1 ln n1 plus n2 ln n1 plus n2 minus n2 ln n2. And we have used the identity of ln of a by b is equal to ln of a minus ln of b here. Okay, so if you apply this identity in this expression, in this equation, okay, then you can get this expression. And from that expression, you can take delta S. You can take this. You can write this delta S as k into n1 plus n2 ln n1 plus n2. Okay, minus n1 ln n1 minus n2 ln n2. So it is. I just take I just took this n1 and this n2 together, and I wrote this as n1 plus n2, and ln of n1 plus n2, that is common, so I have taken it as common, and n1 and plus n2 here, and remaining term is minus n1 ln n1 and minus n2 ln n2. Just rearranging that equation, and after that you can write this expression as delta S is equal to k into ln n1 plus n2 factorial plus n1 plus n2 minus ln n1 factorial plus n1 minus ln n2 factorial plus n2. Okay, this is just by using that Stirling's formula. You have a Stirling's formula ln of n factorial equal to n ln n minus n. So by using this expression you can write. So if you are expanding this particular expression, you will get n1 plus n2 ln n1 plus n2 minus n1 plus n2. So that minus n1 plus n2 will get cancelled with this plus n1 plus n2, so that you will get finally you will get n1 plus n2 times ln n1 plus n2. Similarly here, if you expand this one ln n1 factorial, if you expand that one by using Stirling's formula, this formula, then you will get n1 ln n1 minus n1, then that minus n1 and this plus n1 will get cancelled. You will get finally n1 ln n1, that is your term. Okay, this term. Similarly you will get minus n2 ln n2. So that is same formula, but I am using Stirling's formula here and rearranging that equation in terms of factorial. And then I can rearrange again that change in entropy as k times ln n1 plus n2 factorial minus ln n1 factorial minus ln n2 factorial. Okay. How? Because this n1 plus n2 can be cancelled by this minus n1 and minus n2. So finally you will get ln n1 plus n2 factorial minus ln n1 factorial minus ln n2 factorial. So that is a final expression. Now if you assume the entropy diminished by a factor of k ln n factorial, if you consider the entropy is diminished by k ln n factorial, okay, then that is number of microstate is reduced by a factor of n factorial. You know that k ln n factorial, which means that you are having entropy which is k ln omega. Entropy is nothing but k ln omega. Okay, so your similarly, if you consider the number of microstates, then that microstate should be uh, reduced by a factor of n factorial. So if you are considering that entropy relation, so S equal to k ln omega, okay, S equal to k ln omega. So if you put omega, instead of omega, if you put omega by n factorial, then you can write this as k ln omega minus k ln n factorial, right? If you are having one n factorial term here, like this, if the microstate, number of microstate is divided by n factorial, then your term will become k ln omega minus k ln n factorial by the role ln a by b, ln a by b equal to ln a minus ln b. Okay, so we have to get this term in our expression. K ln n factorial is the additional term that we have to get. So that in order to get that term, we have to have the microstate divided by n factorial. Number of microstates should be divided by n factorial or reduced by that n factorial. So okay, so when you consider that factor in our expression, so actually we have to get k ln n factorial in our expression to remove the Gibbs paradox. Okay, so our entropy should have should be like k ln omega minus k ln n factorial, which means the entropy should be diminished or decreased by this factor. Okay, Then for that we have to consider the number of microstate has to be divided with n factorial. Then only we'll get an additional minus KLN n factorial in our entropy term. So that we consider a new number of microstate, that is omega star, which is equal to omega by n factorial. Then S star, that is the new entropy, that will be equal to k ln omega star, that is equal to k ln omega by n factorial. Then you will get k ln omega minus k ln n factorial. That is the new entropy by considering the number of microstate divided by n factorial, or it is reduced by a factor of n factorial. If you consider that, then you will get a new entropy S star, which is equal to k ln omega star, which is equal to k ln omega by n factorial. That can be written as k ln omega minus k ln n factorial. So now we have an additional term in our entropy equation. And now we will see how this additional term contribute towards the uh, removal of or solving towards solving the Gibbs paradox. So S star, that is new entropy, that is equal to old entropy, okay, that is S, that is equal to k ln omega minus k ln n factorial. Now if you consider change in entropy, if you consider change in entropy delta S star, change in new entropy, that is equal to change in new entropy of mixing minus total entropy, that is S1 star minus S2 star. So I think this should be S1 star minus S2. Here S1, yeah, this should be okay, this should be plus, and okay. So total entropy you have to subtract from this mixing entropy of mixing. That will be the change in entropy. So all these are new, okay, new entropy, okay, change in entropy, okay, new entropy, that is equal to change the new entropy of mixing minus total entropy, or total new entropy of mixing, total new entropy mixing. So this can be again further, it can be reduced as sm is the old entropy of mixing, okay, without this term, okay, additional term. So that is sm minus k ln n1 plus n2 factorial, that is the uh, Sm star, then minus S1 minus k ln, this is n1 factorial, and S2 minus S2 minus k ln n2 factorial. Okay, so this all these terms Sm star representing xm minus k ln n1 plus n2 factorial, S1 star representing x1 minus k ln n1 factorial, S2 star representing S2 minus k ln n2 factorial. So for all those old entropy, we are having all those old entropy which are Sm, S1 and S2. S1 and S2 are entropy of first gas, and S2 is the entropy of second gas, and Sm is the entropy of mixing. All those things are old entropies. All those quantities are diminished by these factors k ln n1 plus n2 factorial, k ln n1 factorial, k ln n2 factorial, with when you consider your number of microstate is divided by n factorial. Okay, now we'll see how that can remove the Gibbs paradox. Now again, if you consider the same system, then you can write the change in entropy in new uh, microstate, that is omega by n factorial, that is delta S star will become Sm minus S1 plus S2 minus k ln n1 plus n2 factorial plus k ln n1 factorial plus k ln n2 factorial. Then delta S, this delta S star, this is equal to delta S, this is old entropy change minus old entropy change is nothing but this quantity Sm minus S1 plus S2, or Sm minus St. Okay, this we have discussed in the last class. So if you want an explanation of this, then you can just visit or check that video. So this is our old entropy, and with this entropy or this term we are having additional terms minus kln n1 plus n2 factorial plus kln n1 factorial plus kln n2 factorial. Now if you consider that again, then you can write delta s star is equal to delta s minus kln n1 plus n2 factorial plus kln n1 factorial plus kln n2 factorial. Okay, so this is your old change in entropy. Okay, now substitute for delta s from equation 7. Okay, from equation 7. So equation 7 we have here equation 7. I think, oh sorry, equation 6 here. So equation 7 is the first equation. We have written here, yes, this one. Okay, here you just subtract this one. This one is equation 7. You just substitute this equation 7 in that expression. Then you can get delta s star is equal to, this is delta s, you substitute delta s in that equation. Then you will get delta s star is equal to k ln n1 plus n2 factorial minus k ln n1 factorial minus k ln n2 factorial minus k ln n1 plus n2 factorial plus k ln n1 factorial plus k ln n2 factorial. Okay, so just substitute that, and the sum of those terms, all those terms you can see here, k ln n1 plus n2, this will cancel, minus k ln 2 factorial, this will cancel, and this also will cancel, and finally you'll get delta s star that is equal to 0. So now you can see the entropy change for identical gas which is equal to 0, and that is same as what we are getting from thermodynamics. Okay, now it is okay. Now when the entropy is modified, you can see when the entropy is modified by equation S star equal to S minus KLN n factorial, we get same result as thermodynamics in thermodynamics. So when you modify the entropy equation, or when you have a decrease in entropy equation by a factor KLN n factorial, then you will get delta S is equal to 0 for identical gases. Mixing after mixing identical gases, if you calculate what is the entropy change, then you will get the entropy change is equal to 0, because it is a reversible process, that delta S should be equal to 0. Now it is satisfying the condition which we have from thermodynamics. And in case of dissimilar gases, now we have changed the entropy equation by this. Okay, this expression. Now if you calculate for dissimilar gases also, we should get delta S should be greater than 0. For dissimilar gases, entropy change should be greater than 0. Then that also we have to derive by using, or we have to get by using this expression. Then only we can say entropy is equal to S, which is not equal to S, but, or which is not equal to k ln omega, but it is k ln omega minus k ln n factorial, this term. Okay, so for that we have to check whether this entropy equation will give you delta S greater than 0 for dissimilar gases. When you consider mixing of dissimilar gases, it is a irreversible process. Then you should get delta S as greater than 0. So the number of microstate, if you consider for mixing, after mixing, if you consider number of microstate, then that is omega 1 star into omega 2 star. So omega 1 star is the number of microstate for the first gas. Omega 2 star is the number of microstate for the second gas, and mixing, after mixing, the total number of microstate will be omega 1 star into omega 2 star. Okay, then if you divide this, so these are new number of microstates. So the old microstates are omega 1 and omega 2. They are divided by n1 factorial and n2 factorial to get the new microstate omega 1 star and omega 2 star. And if you multiply that, then you will get omega 1 into omega 2 here. That is the omega m, that is mixed. In the case of mixed state, what is number of microstate? That is omega m divided by n1 factorial into n2 factorial. Okay, so now you know this. After mixing, sm star will become sm minus kln n1 factorial n2 factorial, because when you substitute, when you calculate the number of microstate with this expression, sorry, the entropy with this expression, because your number of microstate will become omega m star, that is equal to omega m by n1 factorial into n2 factorial. So entropy is nothing but k ln omega. So if you substitute k ln omega, I will just do that here. Now your omega is omega m star, and omega m star new number of microstate in the mixed state. So that is equal to omega m, that is the old number of microstate in mixed state divided by n1 factorial n2 factorial into n2 factorial. So when you calculate entropy for this system, new entropy after mixing, that will be equal to k ln omega. So that is k ln of omega m divided by n1 factorial into n2 factorial. So if you take this expression, then it is k ln omega m minus k ln n1 factorial into n2 factorial. So I think you might not be able to see that. So you can see from here, this is the expression. So you can see omega m star is equal to omega m by n1 factorial into n2 factorial. So mm star is sm star is now k ln omega. Omega is nothing but omega m star. We have to substitute. Then omega m by n1 factorial n2 factorial. Then it is k ln omega m. Okay, minus k ln n1 factorial into n2 factorial. So that is this expression. And if you substitute all these values, so delta S star, if you consider delta S star will be equal to Sm star minus S1 star plus S2 star. That is the entropy change. And then you substitute what is Sm star here, that is Sm minus KLN n1 factorial n2 factorial. And S1 star we already calculated. S1 star is equal to minus, then minus is taken outside, this S1 plus KLN n1 factorial minus S2 plus KLN n2 factorial. That you will get S1 star is nothing but KLN omega. So here you will get KLN omega 1 minus, for the first case, KLN n1 factorial. This is S1 star, then S2 star you can get KLN omega 2 minus KLN n2 factorial. So this term is S1 and this term is S2 that you have to substitute, then you will get this entire term. Okay, this entire term. And then delta S star you can write Sm minus S1 plus S2, Sm minus S1 plus S2. All other terms will be vanished. You can rearrange this ln n1 factorial. This you can write it as ln n1 plus ln n2, because ln of ab equal to ln of a plus ln of b. Then if you subtract that, this is minus and these two are plus, so these terms will get cancelled each other, and then you will get Sm minus S1 plus S2. That is same expression that we got for the calculation of dissimilar gases. Then delta Sm star is same as delta Sm. Okay, so in that case there is no change, which means that the entropy expression or entropy equation that we just found, that is same. Okay, which will work for both gases, identical as well as dissimilar gases, similar as well as dissimilar gases. And when you consider that term, we also have to consider the same time we have to consider, okay, let me visualize that. Okay, we have to consider the equation for entropy. When you consider the equation for entropy, okay, so let me take this out because it is not visible for you. So when you consider the equation for entropy, you can see here entropy equation for entropy. You can see if you substitute as new entropy equation, and then if you solve for equation for entropy will become, if you are considering omega as omega by n factorial, then you can get the expression for entropy as S equal to nk v by h cube 4 pi m e by 3n 3 by 2 plus 3n by 2. So in this expression, you will get an additional minus k ln n factorial, because you are considering now omega equal to omega by n factorial. Then you will get for entropy you will get an additional term minus k ln. I will write it here. Then whether it is visible, I will check. So you are getting you are having entropy as omega equal to omega by n factorial now, new entropy. Okay, so this if you rearrange this, then you will get in entropy equation you have k ln omega minus k ln n factorial. So this factor will be an additional term, minus k ln n factorial will be an additional term in entropy equation. So for ideal gas also, this minus k ln n factorial will come as an additional term for the ideal gas equation. Then if you can rearrange that expression, because this is minus k ln n factorial minus k ln n factorial. So if you rearrange that, then you can take this nk ln v by h cube 4 pi me. This is 4 pi me by 3n all raised to 3 by 2. This is same expression, plus 3 by 2 nk plus 3 by 2 nk minus nk. This you can write it as nk ln n. You can write this as, you can rearrange this ln n factorial, you can write it as n ln n minus n, right, by using Stirling's formula. So that you can substitute, instead of k ln n factorial, this will become k n ln n, okay, plus nk. Now finally you will get S equal to nk ln v by h cube 4 pi me 4 pi me all raised to 3 by 2 4 pi me by 3n all raised to 3 by 2 plus 5 by 2 nk that is the final expression. That is the final expression that you will get from this equation 5 by 2 nk, because you are having 1 nk here, you are having 3 by 2 nk here. Then you will get 5 by 2 nk as an additional term, and you have nk ln n here, nk ln n here, so that you can take here. So this nk ln will be common, and an additional only one additional term n will come, right? Additional term n will come here. I think this one will be yes, this will be n ln n, so that will become nk ln n here, and that is a minus term. Okay, so minus n also will come, I think. So this one is minus ln, okay, ln n will be there, so ln, yes, 3n will be in your final expression. You will be getting minus ln n, so you can write it as here n here, so this will be, I think this will be n square. Sorry, this will not be coming as a 3 by 2. Outside you will be having one n, additional n. in this here we will be having one additional n outside, okay, not inside that. Okay, so that is the final expression, and this expression is called as Sackur-Tetrode equation. This expression is called as Sackur-Tetrode equation. So you can see from here, Sackur-Tetrode equation. So I will just rewrite that expression here for entropy. So this entropy expression will become, after modification of that number of microstate with omega by n factorial, your entropy expression will become ln n v by h cube times n. Okay, then 4 pi me divided by 3n all raised to 3 by 2 plus 5 by 2 nk. So this is the Sackur-Tetrode equation. So there is one n missing this expression. Okay, so that is coming from this part. Okay, so nk ln n, this is nk ln n. So if you take nk as common, then you have minus ln n here. Okay, minus ln n here. So that minus ln, if you take as with this term in this bracket, then you have to take it as a denominator. This n will go to denominator, then it is like an ln a by b form. So that is coming as v by h cube times n here. Then 4 pi m by 3n all raised to 3 by 2. So that is the Sackur-Tetrode equation after rearranging omega with omega by n factor.